Hello, my name is Zahra Ashktorab, and I'm here to present our research on fairness evaluation and text classification, machine learning practitioner perspectives of individual and group fairness. This work was conducted in collaboration with some other folks listed here, and will be presented at the CHI Conference on Human Factors in Computing Systems in Hamburg, Germany. We know that algorithms play a role in furthering social inequities, and that's a problem. From machine learning recognition systems and autonomous vehicles that have been less effective in recognizing darker skin, search engine results that have reinforced representation bias, and professional networking sites were discovered to recommend male-sounding variations of names when female-sounding names were searched. There are many existing tools to help users make decisions about the fairness of a model, so a human's perceived fairness plays an important role in the decision-making tasks. Fairness is highly contextual, and many studies relevant to intelligent user interfaces are interested in how humans make judgments about fairness. Prior work in fairness and text classification identified bias in toxic text classification when identity tokens are disproportionately used in toxic comments. For instance, if the word gay appears more frequently in toxic comments, a model might tie it to toxicity. We used a set of 50 common identity tokens identified in prior work to build our fairness metrics for a toxic comment classification dataset. In our study, we investigate how machine learning practitioners interact with fairness tools in text classification. This includes exploring views on group and individual fairness and the strategies used to determine the fairness of the model. Which brings us to our research questions. How do diverse yet status metrics impact user perspectives of the model? What kind of exploration strategies do machine learning practitioners use to determine model fairness when presented with an interactive fairness tool that allows custom inputs? How are users' fairness decisions formed as they explore an interactive fairness tool with performance and varying fairness views? Our methodology consisted of 4 parts. We recruited individuals who work on AI systems from both our institution and other institutions through word of mouth. Participants were asked to go through 4 different tasks, starting with a task in which they viewed the overall performance of 3 models, in which we referred to as Model A, Model B, and Model C, and asked to give their opinions. They were then able to see the performance on group filtered views of the data, and then they saw performance on individual fairness sentences in the data. After each of these phases, they were asked to select which model they would deploy based on the information they just viewed. This is a more in-depth view of Task 1. In this task, we showed users accuracy metrics. Our aim was to explore how users determine the best model to deploy without being presented with the fairness metrics. In Task 2, users were shown subgroups of the data based on words describing minority identities. These subgroups were defined by filtering the data set for examples containing particular words. We selected groups of words related to various identities such as sexuality, race, ethnicity, and religion. We have an example on the slide in which the text has been filtered for mentions of African, African American, and Black. In Task 3, we allowed users to examine various pre-selected sentences and see how the model changed its classification when identity tokens in the sentence were changed. One of the sentences is seen on this page. The figures of the interface that prompted users for the custom examples in the exploration view can be seen here. Users were able to experiment with 4 different types of interactions: the pre-populated group view, the pre-populated individual view, the custom group view, and the custom individual view. Participants had the chance to inspect the individual and group views presented to them in the previous task, but with their own custom inputs. They were instructed to conduct 10 additional model checks to ultimately make a decision as to which model to select, choosing to either see the performance of a selected subgroup or see the performance between examples conditioned on a single word. We presented 3 models to the users. Model A, prioritizing balanced accuracy by enforcing an equal number of toxic and non-toxic samples. Model B, aiming for individual fairness by treating similar inputs similarly. And Model C, striving for group fairness by treating inputs with the same identity tokens equally. 24 participants from industry and academia selected different models based on the presented view. When only shown accuracy metrics, the majority chose Model A. After viewing the group view, the selections were split between Model A and Model C. The majority selected Model B after seeing the individual view. After exploring with both pre-populated and custom inputs, the participants were split between Model A and B. We were also interested in exploring the reasons why individuals made their selections. We asked users to explain why and coded for each model selection. Because of time limitations, I'll only be going through reasons for the most selected model after each task. After the first task, majority of participants cited prioritizing toxic accuracy when selecting their model. After the second task, when participants were shown group view, participants cited prioritizing non-toxic accuracy. One participant said, while Model A performs best on toxic comments, it is also clearly flagging many normal comments that mention minority groups as toxic. Model C seems to help alleviate this problem at best. After seeing the individual view, participants cited identity changes and the impact that they had on the model. And similarly, after the exploration view, participants cited identity changes not impacting the model as the reason for their model selection. We also identified different categories of groups that users explored in the group view. We were able to identify 3 groups: the same identity category but with different identities, same identity category and similar identities, and different identity categories. The majority of the users chose words related to the same category like race or gender but with different identities, while a smaller percentage explored the same identity category with words belonging to the same identity within that category. A very small number of users grouped words that were completely different identity categories together. We had 97 custom explorations where users created their own sentences or modified pre-populated examples. These explorations were categorized into unambiguously toxic and unambiguously non-toxic groups. Users used more of their own words as they became more and more experienced with the tool. One participant said, "I aim to test the model's ability to navigate nuance in language to see if honest, respectful discussion of potentially loaded topics would result in toxicity flags." We also asked users reasons for individual exploration and did thematic analysis on those reasons. Many themes emerged that are listed in this table, including groups that are historically discriminated against, using ambiguous words to see how the model responds, or words and sentences influenced by current events. Based on our findings, we're able to offer design recommendations to improve fairness in language tasks. The first recommendation is to provide additional context and metadata to assist users in their decision-making, such as showing sentences and documents that appear before or after the document being evaluated for fairness. We also recommend including similarity indicators to help users understand how similar sentences and documents that they have chosen are to one another when there is overlap in the sentences based on the words that they have selected. We also recommend including an asymmetrical counterfactual metric to guide users to test those kinds of sentences that may be toxic for certain identity tokens and non-toxic for others, and to better understand how the model is making predictions based on different identity groups. We also recommend considering the risks associated with overpredicting and underpredicting, depending on the situation, to balance accuracy and fairness in models, and to provide simulated-based approaches to support practitioners in their evaluation of fairness and explore different facets of the data to uncover potential bias. Including additional group fairness metrics such as equalized odds violation to help users better understand how their model may be biased against certain identity groups is another recommendation that we make. And to also recruit diverse team members with people from different backgrounds to identify potential blind spots and select fairer models. In conclusion, our study identified strategies for determining fairness in NLP models and offered recommendations for improving front-end tooling. By implementing these recommendations, we can work towards more equitable and inclusive NLP models. We hope this research inspires further investigation into user perspectives on fairness and promotes the development of more just and equitable technologies. Thank you.